Yeah, okay, so thanks a ton for the introduction and the invitation to speak here. It's interesting being in this room, like after seeing it on YouTube and everything. So um, yeah, I'll be talking about how to count automorphic representations with a certain cohomological components at infinity on unitary groups. And let me just mention that this is joint work with Mathilde Gervais-Gauthier, who was here, so I guess maybe a lot of you might know her. So before I get into the math, I just have some kind of color coding scheme that I like to use in talks. So there'll be certain things that'll be highlighted in gray or orange. And the gray things are just things that they're sort of not good to pay attention to the first time you're hearing about something. They're just technical details that get in the way of understanding. And they're just on the slides to make sure that there are no lies. And the orange things are things that are not going to be explained fully. Or like there'll be things that I'll explain a little bit later in the talk and I'll only explain them sort of intuitively and precisely. So as an outline of the talk,
I mean, I thought that was Princeton colored.
Black is normal. Black and blue and everything else are just normal.
Okay.
So just as an outline for the talk, I'll start with a sort of motivation for the problem. For those people that aren't that familiar with like automorphic representations. And then I'll go into a statement of the results. Then I'll go over a background on sort of Arthur's classification, Arthur's endoscopic classification, which is sort of the main technical tool that we're going to be using for this project. And it won't be like a full explanation of how it works. It'll just be like the bare minimum of what's necessary for understanding the next part. So the next part will be a particular inductive analysis using Arthur's classification that lets us solve the problem that we'll talk about. And then if there's time at the very end, I'll discuss some tricks that are useful for the very specific computation that happens here. So unfortunately, I didn't really finish the write-up before coming here. So the details should hopefully be uploaded to archive soon. And I'm really hoping by the end of this month. The draft is basically written except some details of corollaries at the end and maybe like an introduction and some cleanup. So if people want details, feel free to email and I can maybe even just send you the entire draft and warn you which parts are to ignore. And then finally, so this is something that uses the endoscopic classification. So I just have to put this standard warning here that we're not just using the endoscopic classification, we're using it for non-quasi-split unitary groups. So the statements are all published, but there's a lot of unpublished and maybe unwritten. I don't know whether it's written or unwritten, but there's a lot of unpublished stuff that goes into the proofs. So I need to put this warning here. Okay, so let's begin with the motivation. So I'll start with sort of a perspective on automorphic representations. Just like a very quick introduction. Well, I don't know, maybe not an introduction, but like just a quick like everyone on the same page thing. So we'll talk about discrete automorphic representations. So we're going to take some reductive group G over F, and then we're going to look at discrete subrepresentations of the space of L2 functions on this specific quotient. And this is a representation under right multiplication by the adelic points of your reductive group. So of course, these automorphic representations, they have this factorization where like this adelic points of the group are a product of the FV points of the group for every V. So your representation factors, your irreducible representation might factor as a tensor product of irreducible representations of GFV for each V. And the places over infinity in this perspective, they kind of play a special role where the place over infinity tells you maybe the qualitative type of a representation. So maybe whether it like corresponds to modular or Moss forms, whether it satisfies these adjectives of being like holomorphic or quaternionic. And we'll talk about a little bit more later, whether they're like algebraic or cohomological, what kind of role they play in like applications of automorphic representations. So of course, maybe I don't need to justify the subject here, but there are lots of applications of automorphic representations. Just gonna like name drop 3 of them that are more relevant than the others to the specific problem. So the Langlands program says that they have to do with Galois representations. They let you construct these objects called expanders that are useful sometimes in designing computer algorithms. And they let you understand some like interesting cases of locally symmetric spaces and let you say that they have some unusual geometric properties. So when you want to look at an application of automorphic representations to another thing, there's sort of a key problem that you often need to end up answering, which is which combinations of these local factors pi v can you actually tensor together to get something that is actually a subrepresentation of this L2 space? So you can pick a bunch of random pi v, tensor them together, and you won't necessarily get a subrepresentation, but sometimes you will. And that's sort of the main problem that tells you whether something is automorphic or not. And that's what's of interest in all the applications. So we won't be thinking about this literal key problem. We'll be thinking about a much more basic version where what we're going to do is we're going to put local restrictions on a lot of these pi v's just to put some conditions on them. And then we're going to try to count how many things there are that satisfy those conditions. Maybe we won't count, maybe we'll weight our count by a certain statistic. So as you can, this is just like maybe the most basic thing to talk about when you're trying to look at the key problem. Okay, so that's a general perspective. Now I want to go over a little bit more about this pi infinity telling the qualitative type of the automorphic representation. So there's sort of an informal ranking of complexity of automorphic representations based on the complexity of this representation at infinity. So at the very bottom, the simplest things, you can look at discrete at infinity automorphic representations. And this is where the infinite component is a discrete series representation of the group at infinity. So that means you can literally find it as L2 functions on the group, as a subset of L2 functions on the group at infinity. So the sort of next level of complexity is cohomological automorphic representations. So basically, representations of the real group, they have an invariant attached to them called their infinitesimal character. And the cohomological ones are the ones that have the simplest possible infinitesimal character. So the infinitesimal character that basically matches that of a finite dimensional representation. And the adjectives that you say for that are that the infinitesimal character is regular and integral. So after cohomological, the sort of maybe next step on this ladder of complexity is algebraic automorphic representations, where you drop this condition that the infinitesimal character needs to be regular. And then finally, you have general automorphic representations where you can have any kind of pi infinity. So different applications, you need to care about things of different complexity. Sometimes you're lucky and you don't need to deal with the nastiest ones, and sometimes you're unlucky. So for example, like just by the names, if you care about cohomology of locally symmetric spaces, like the sort of like topological cohomologies, then you only care about the first two. You care about the discrete at infinity and cohomological ones. If you care about Galois representations, then you also need to worry about algebraic automorphic representations. And in general, you might need to care about all of them. I don't know, sometimes the applications to physics or like other things like that. And then you're very sad. Okay. So just as an example, we can talk about where the like automorphic representations on GL2 over Q fit in this ladder, just to get a better understanding of this. So just as a reminder, automorphic representations on this GL2 over the rational numbers, these are basically classical modular and Moss forms. So discrete at infinity, it means you're looking at modular forms of weight greater than or equal to 2. So unfortunately, this example isn't perfect because when you look at the things that are cohomological but not discrete at infinity, you actually don't get anything extra for GL2 besides like the trivial representation. And I don't really know any like good classical examples of something that's cohomological but not discrete at infinity. But there are examples on other groups and they are important on other groups. So if you care about algebraic, then suddenly you need to also worry about weight 1 modular forms and weight 1 Moss forms. And if you care about general, then you have to worry about all the insane like transcendental Moss forms.
You don't know that transcendental.
Well, okay, yeah, I don't know. Yeah, but yeah, I guess.
They probably are.
There's not very much known about them. Okay. So, right, so now we can talk about answering this basic version of our key question. How far up this ladder can we go and still start computing statistics? And maybe I'll talk about just a very quick overview of one of the tools that you can use to try to do this. So a very useful tool is Arthur's trace formula, which basically, very roughly, it lets you compute a sum of traces against the sum over the discrete automorphic representations of the trace of a test function against the automorphic representation. So you pick your test function cleverly, you kill ones that don't satisfy the local condition you care about, and you get a weighting by whatever statistic you care for the ones that, that do satisfy the condition. So for discrete at infinity or automorphic representations, there's sort of two tools here. First, there's a sort of a paper of Arthur. It's titled like L2 Lefschetz numbers of something like that. And it basically gives a nice like explicit version of the trace formula in the case where you have discrete series at infinity, but it sort of coarsens the information where you can't restrict the representation at infinity to a single representation. You restrict it to a set of representations, a small set called an L packet. And there's some extra stuff you can do on top of it that was worked out by someone named Ferrari who left math, where you can break up and you can restrict to a single thing. So of course, this is a tool you use to study the problem. It doesn't like completely solve the problem. It reduces the problem to understanding some other things. And for the coarse information, the main other thing you need to understand is these things called orbital integrals. And if you want to do the fine info, then you need to understand and compute explicitly some endoscopic transfers, depending on what you're doing. So depending on which exact statistic you want to look at specific orbital integrals and specific endoscopic transfers. And these aren't easy things, but they're like maybe easier than trying to answer the question straight out. So basically the point is, in the applications, you feed in enough special information about orbital integrals and endoscopic transfers, and then you get information about the statistics problem. So for like, maybe you can talk about exact counts and maybe limiting statistics. So for exact counts, there are many, many, many results for low level and small rank. And I don't have a comprehensive enough knowledge to like fairly summarize them. And for statistics—
I'm sorry, statistics usually has distribution. So which statistical distribution are you talking about here?
Yeah, so what I mean by statistics is you can look at these local conditions, you can send the local conditions to infinity in some sense, and then you can ask about like the asymptotics of how many representations there are. Or you can, there's some parameter of the representations that satisfy the conditions, and you can look at some distribution, limiting distribution of what this parameter is. Does that answer the question?
Not really, but go ahead.
Sorry, okay. Yeah, so I mean, statistics is just like, you can count, like, so you can think of counting modular forms of a certain level, right, at a certain weight. And you can see that as you increase the level, the number of modular forms is some like polynomial in the level, right? And it's like the asymptotic, the degree of the polynomial and like the leading coefficient, questions like that. Does that help more, or is that still? Okay, well, okay, maybe okay. Right. So basically the finest statistics you can compute are built out of this work of Shin-Templier, where basically you get like, you get the leading term exactly for any of these averages. And well, so Shin-Templier basically did it with the coarse information, and then you add this extra stuff by Ferrari, and you can do it with the fine information also. So the next step is you want to look at cohomological representations. So the tool you have to use here is you have to use Arthur's endoscopic classification. And there's sort of an inductive argument by Taibbi that's sort of like the full way to use Arthur's endoscopic classification to solve these counting problems. And basically you need to understand the same two things that you did before. And if you want to do it like in full generality, there's another thing you need to understand called stable transfer, which is much more difficult. But again, like in special cases, you can say enough about this to get results. So for exact counts, so Taibbi used this to get exact counts at level 1, and there's other work that use it to get exact counts at level 1. And then if you want to look at these statistical problems, or you want to look at like asymptotics and limiting distributions, basically one place to look at that sort of has a good summary of how to do it for just upper bounds is a paper by Marshall and Shin, and other stuff by Marshall and Gauthier that also get some upper bounds. So, and this work basically tries to use the full details of this inductive argument to get more than upper bounds, to try to get exact asymptotics in lots of cases. And we try to get upper bounds in cases that maybe weren't there before also. And then finally, beyond is very difficult. And I think there's like a math overflow post that says that if you just want literal like asymptotic counts of wave one modular forms of level n, maybe that's not even proven. So it's just like very hopeless and very difficult to go beyond like cohomological at the moment. And maybe people need like much fancier techniques. Okay, so that finishes the motivation. So now if there are not any questions, I'll move on to talking about the precise result that we have. Okay. So here's the precise result. So first of all, there's like a lot of orange here, so it's not going to be explained on this slide. I'll discuss it in detail. So we're going to let E over F be some unramified CM extension, and G an unramified inner form of the quasi-split unitary group of rank n related to E over F. So then we're going to fix some cohomological representation on G infinity, the representation in the second nice class. We're going to pick an ideal of the ring of integers of F that's only divisible by prime split in E over F. And we're going to pick some unramified test function at some set of places S not dividing n. And then for certain pi 0, we have this asymptotic statement over here. So before we get into the details of like what any of this means, because it's like pretty daunting to see on the slide, let me just make a note about all the conditions of this theorem. So first of all, there's some pretty strong conditions here. So E over F needs to be unramified. This n, this sort of like level parameter, it can only be divisible by split primes. So we can't deal with the non-split primes here. And this pi 0, there's a condition on it. It doesn't work for all pi 0. It only works for a certain class of good pi 0. And what is this class of good pi 0? Well, it's explicitly described. There's a combinatorial classification of these cohomological automorphic representations of unitary groups. So it's you can feed in the parameter that determines some pi 0 according to this classification, and you can read off whether it's good or not.
Pi 0 need not be tempered, right?
Pi 0 need not be tempered. Yeah, that's sort of the whole point. If pi 0 were tempered, then it's discrete series, and we already know a lot more. Okay, so now let's get into the details of what exactly this equation is saying. So let's just pull it out separately and let's talk about all the pieces. So first of all, this is an asymptotic statement, and it's asymptotic in sort of three things. So there are like three things in this big O. So first, it's asymptotic on this n, this ideal that we chose, this sort of level restriction. It's asymptotic in the number of places that our unramified test function is in. And it's asymptotic in the unramified test function. So there's this parameter kappa of FFS, and that's sort of some sort of measure of how big the support of FFS is. Okay, so what is the n doing in here? So what the n is doing in here, so what is this sum over here? So this sum, we're looking at all automorphic representations with the component at infinity matching a certain pi 0. Then what we're doing is we're looking at the fixed vectors of the away from infinity part on the level subgroup determined by n. So this is sort of what we're doing here is we're counting fixed vectors in an automorphic representations with a certain condition. So that's like counting automorphic forms. So we're giving a count of automorphic forms of level n. And this is telling you what the asymptotics are in the count of automorphic forms. So sort of the main term is going to grow like n to whatever this r is times whatever this constant is, and the error term, there's going to be some kind of power saving. So the c and these a and b are sort of constants, they're not explicit, but I think you can show that c is necessarily greater than or equal to 1. So that's the sort of saving that you have in the error term.
And just to be clear again, these are violations of naive Ramanujan.
These are violations of Ramanujan, right? So like if you assumed Ramanujan, then like these shouldn't exist at all because these pi 0 are non-tempered. But this is sort of saying that some of them do exist, and it's kind of telling you how many of them exist. So what is the F doing? The F is the part where we don't just allow counting representations, we allow averaging a certain parameter of the representations.
Sorry, are they actually violations? Or maybe these guys are not necessarily customable. Are they just?
Oh yeah, sorry, they're discrete. They're just discrete, so they're not necessarily violations. I'm sorry. Yeah, they're just discrete.
Well, you may be compact. You said quasi-split, right?
I said quasi-split. Yeah. Well, I mean, okay, so this thing doesn't need to be, the G doesn't need to be quasi-split, it's an inner form.
Okay, then.
But it can be quasi-split.
then cuspidal is meaningless. So,
Right, in that case, yeah.
so it's counting.
Yeah.
But it's counting not naive Ramanujan, so that's why you can get it in a way.
Yeah.
Like you can't do weight one, as you said.
Yeah.
Because that's tempered but not discrete series.
Yeah, so FS is telling us the sort of parameter that we're averaging at the automorphic over these automorphic forms. So we're weighting by this trace of pi s of Fs. And Fs is an unramified function, so it's basically telling you some kind of polynomial in the Satake parameters of the S components. So if you don't know what those are, you can think of these as like, if you look at modular forms, you have the Hecke eigenvalues, and this is some like sum of powers of the Hecke eigenvalues. So you can think of this as some generalization of maybe computing a moment of the Hecke eigenvalues of the like weight of the level on modular forms. And of course, so we can do that, and we know how the error term depends on like which moment we're computing. And when you think of the moment, as you get to bigger and bigger moments, k is sort of going to grow linearly in how big of a moment you're looking at. Okay, so what are these constants? They're explicit formulas for these constants. In terms of Fs, there's some integral you can write down that tells you what m of Fs is. And m and r, you can compute them from the combinatorial data that determines pi 0.
Can you show that MFS is not 0?
Yeah, MFS should not be 0 for reasonable Fs, but this m pi sometimes will be 0.
So it's subtle with they are. I mean, even in a unitary 3 variable in Rogowski, it depends on what your group is, whether there's violations of Ramanujan.
Yeah, there's some weird like parity condition.
But that's to answer the question. It not be that you're in some situation where it's like a division algebra with some property where you don't get these guys.
Yeah, but anyway, yeah. So the m pi 0 can be 0. The Fs should not be 0 for like reasonable Fs. Okay, and there are 3 more constants, is A, B, and C, and these are inexplicit constants. Basically, this result is bootstrapping off the Shin-Templier result, and in that result, there are these A, B's, and C's that are inexplicit. So because we're ultimately relying on that at the bottom, we don't get explicit control over these.
In theory, would it be possible to compute these, or is it actually ineffective?
In theory, C and B maybe you can compute, or I think I know how to compute C and B in theory, but it's a lot of work. I have absolutely no idea how to do A.
So you're using their result on another group, is that right?
Yeah, we're using their result on lots of groups and inducting off it. Yeah, for discrete series. Yeah. So B is if you like understand orbital integrals well enough of like how they grow as the Fs gets bigger and bigger, then you get B. A, you need to understand orbital integrals of the unit element really well in the Hecke algebra, and C is like keeping track of things very carefully. So, okay. So I think I need to give a little more intuition on what exactly these constants are and how big they are. So first of all, I have to say a little bit about these pi zeros. So these pi zeros are constructed from a process called cohomological induction, and from complex levies L of this group G. So to every pi 0, you get associated a levy that it kind of comes from in some way. And this is not the Langland's classification. It's like another way that it comes from a levy. These are complex levies. They're not defined over the real numbers. So this is like another classification. So basically the levy is a bunch of blocks, and the list of block sizes basically tells you the Arthur SL2 that's associated to pi 0. So the Arthur SL2 for the Arthur packet that the pi 0 lives inside. And you might complain, well, pi 0 can live in multiple different L packets, but the point is there are multiple different ways to realize pi 0 as a cohomological induction, and those sort of line up with each other. So the good condition is basically that you can realize pi 0 in a way where this L, all the blocks that aren't of size 1 are distinct odd sizes, and that's what our good condition is. So basically the Arthur SL2 decomposes into a bunch of trivial representations and then a bunch of distinct representations of odd dimension. So what is R pi 0? So R pi 0 is a dimension of a parabolic. You construct it out of L in some complicated way. There's a parabolic subgroup of like GL capital N that you construct in some complicated way out of L. And then you need to replace some blocks of the parabolic with like single things, and you compute a dimension. If you are familiar with the work of Marshall and Shin, it's basically the same thing that they have there, where there's some modifications for blocks of size 1, 2, and 3. So basically just like inputting the specific bounds they have and using them somewhere, and that's where this R pi 0 comes from. So basically the key point is that it's going to be less than or equal to n squared. It's going to be equal to n squared when the representation is tempered, and you get some, and it's less than n squared when the representation is non-tempered. So n pi 0 is going to be a dimension of some finite dimensional representation of some smaller GLN, and it has a certain highest weight that you take the infinitesimal character of your cohomological representation, and then you make that infinitesimal character bigger in some way by adding some linear combination of fundamental weights, and the coefficients on this linear combination of fundamental weights are approximately the size of the blocks that are the blocks of each block of size bigger than 1 corresponds to one of these coefficients. So, and depending on like how these blocks interact with the pi naught, that's like which fundamental weight they're associated to. So that's sort of a flavor of where all these numbers come from. We can also look at a specific case where it's like more easy to state what all this combinatorics is. So we can look at un minus 1, 1, or a bunch of different un minus 1, 1s at all the infinite places. So we're going to assume that degree of f over q is d, g infinity is un minus 1, 1 to the d, and pi naught is just going to be like a parallel thing, like a diagonal thing. That's the same cohomological representation in every infinite place. So then the parameterization of cohomological representations of un minus 1, 1 at the infinitesimal character of the trivial representation. There's certain ordered partitions of n. These are the blocks of that levy. But basically one of these blocks is marked, and every block that isn't marked needs to be size 1. And that's like that's the one in un minus 1, 1. That's what it does. So it's very restricted where exactly these can come from, or you can realize them all as coming from very special levies. The good class is, of course, that this marked index needs to be odd. As before, all the blocks that aren't 1 need to be odd. And well, they're just explicit formulas for R pi 0. So this is, again, you take it's some dimension of some parabolic with some modification for the blocks of size 1. And C pi 0 is basically the dimension of some representation. And in this case, what we do is the fundamental weight is where the non-1 entry in this partition appears in this tuple. So that's a specific fundamental weight you look at. And you take the dimension of that multiple of that fundamental weight. So as well, there's some interesting things here. So first of all, you can varying where this non-1 entry is, where this AM is, like which order this partition is in, is kind of like varying the cohomological representation within an L packet. And for discrete series L packets, like whichever representation of the discrete series you pick at infinity, the sort of abundance of these automorphic representations with that component at infinity is the same. But here, interestingly enough, it's not the same, right? So like, as you change this fundamental weight, these dimensions are changing, right? So as like M gets closer and closer to the middle, you have more and more automorphic representations with that particular component at infinity. And if M is far away from the middle, then you have fewer. And finally, in this odd D case, you have this even weirder thing where this like dominant term can disappear for certain ones. There's like a parity condition. So it's not just like the fraction of how many representations there are differs, like whether there is like a meaningful fraction among all of them can also differ. So like somehow the different elements of the L packet can behave very differently when you're counting automorphic representations. So I just want to say that the second thing, maybe it, if you think about Arthur's multiplicity formula, it shouldn't be too surprising. So remember in the statement, what we're doing is we're restricting to representations where the only ramified places are split at finite places. So the character you assign to them in the Arthur packet is trivial at all those places. So what that means is the character assigned to the Arthur packet at infinity also needs to be trivial for there to be multiplicity in some kind of like when pi is in the dominant contribution for the A packet. So that's sort of where the 0 is coming from. The 0 is basically a consequence of Arthur's multiplicity formula. Okay. So that's sort of the statement, all the intuition for a kind of like main like exact asymptotic. Are there any questions? Okay, so we also have a much more general upper bound where you can remove some of the conditions. So we can look at the same setup and we can allow E over F to be ramified now. And we need to pick a set of places containing all the ramified ones. And we have to pick a sort of weighting function satisfying a technical condition. And then we can look at arbitrary pi 0 and we get the same count with an extra weighting factor here. And we just get an asymptotic upper bound instead of an exact asymptotic now.
I'm a bit worried about this positive statement. In
Yes.
Arthur's work, you certainly can't choose a positive test function because he has to collect the parabolic terms, which should be on the geometric side. They come to the spectral side because he doesn't know the trace class conjecture. Although it's known, he doesn't use it. So you can never put absolute values of positive. So in this case, why? I guess if you discrete series, you're just making a comparison from the group you're moving from. Can you just say a word? You say a positive test function.
Yeah, okay, so positive test function, what does that mean? So what this means is that, I hope this doesn't run into the issue you're talking about, but it means that if you look at all the endoscopic transfers of this test function, you can pick them so that their traces are positive on all unitary representations.
Okay, so it's not that you're getting some convergence by positivity.
It's not convergence by some positivity. We're just using it to be able to like push some absolute values around and move them between sums in the right way. So basically, but this is something to be worried about because these such functions, they exist by some kind of surjectivity statement of endoscopic transfer to like all the things at the same time. And but the point is, I don't know if any explicit construction of anything like this. I'm maybe like 60% certain that if you take like some kind of correct like compact matrix coefficient for like generic supercuspidal representation, then it should work. But so maybe not knowing any examples is like a function of my ignorance instead of like a function of like it actually being hard to construct examples. But they definitely like exist like abstractly. So basically you can think of this as some inexplicit weighting factor that we're forced to add to deal with these ramified places.
In Arthur's original paper, when you have discrete series, once you have discrete series, then things are much more under control. It's just in generality.
Yes.
He's using Langland's analytic continuation as a black box. So that he has no a priori. In Selberg's derivation of the trace formula, he doesn't know bounds until he's written down enough test functions to put in a positive test function. But Arthur avoids that because he's always only comparing to do while you're doing analysis.
Yeah.
So I think Shin-Templier deal with this in their paper. Because they assume it's discrete series. So
So at the bottom, we're going to only be dealing with discrete series at infinity. So like a lot of the analytic difficulties are going to disappear. Like that's sort of the.
You have vanishing of various orders.
Yeah, everything vanishes and all the sums work out and converge. And this is not like some analytic thing. This is just like some inequality thing where literally we want to move an absolute value inside a sum, and like this is what lets us do it. So okay, so there's some weird weight factor that lets you look at unramified, like ramified unitary groups. So and then finally, well, this is the work in progress that's sort of delaying us posting it. We're trying to compute the implications of this result to a lot of expected corollaries. So first of all, for those people that are familiar with the Shin-Templier work, because we inputted that work at the bottom and we were able to preserve their error term, we're expecting to get the same kind of corollaries that they got. So we should get some kind of Sato-Tate equidistribution in families. Like if you look at the representations at a level n, and you look at some long list of primes, and you look at all the Satake parameters at those, and you like increase the list of primes you're looking at and the level in some diagonal way, then you'll get some kind of Sato-Tate distribution of what these Satake parameters are. And that's actually going to be like a different Sato-Tate law from the expected Sato-Tate law from that group, because you have this non-tempered thing at infinity, and there's some intuition that means that it's coming from a smaller group. So it's going to kind of be like the Sato-Tate distribution for a smaller group.
Then GL2 would be like CM forms.
Yeah, something like that. Yeah. So, I mean, this is a little bit more speculative because we haven't very carefully gone through this argument and seen whether anything breaks, but Shin and Templier were also able to get some statement of like low-lying zeros of L functions and their distribution and families, and this is something we're going to try computing. So the next thing is basically the Sarnak-Xue density hypothesis. So what this is saying is that if you have an automorphic representation, so it feels really weird talking about this here, but if you have an automorphic representation with a certain component that's non-tempered, it's a measure of how non-tempered.
You're not disproving it, that's fine. You're disproving it, I'll leave.
Yeah. So it should tell you that there are not too many automorphic representations with a component that's too non-tempered. So too non-tempered means that the matrix coefficient decay is too slow on the group. And if you fix that condition at some, where you want to look at automorphic representations with the component that has matrix coefficient decay that's like slower than some level, and you want to increase slower than some bound, you want to look at how many there are of a certain level, increase the level, and there should be some bound on how fast that grows. So in our language, this is just saying that this R pi 0 is going to be small enough depending on the matrix coefficient decay of pi 0. So there's some annoying like contest math inequality that you have to do to actually check that this works. And we're not very good at contest math, so that's like slowing us down by a lot. But we do have many cases that aren't in the literature, although I'm hesitant to claim that those are new cases, because I don't think we're going to get anything beyond what you get if you generalize this Marshall-Shin result to bigger unitary groups. If you try running the Marshall-Shin argument to bigger unitary groups, and they just didn't bother writing out the implications maybe, but I don't expect to get anything better than what would happen if you do that. So it's like many cases that are not in the literature, but maybe it's like too much to claim that they're new cases. Okay. And then finally, there's this Matsushima formula that tells you that if you look at like towers of locally symmetric spaces corresponding to these levels and these groups, then the different HPQs of these towers should correspond to automorphic representations with specific cohomological components at infinity. So this should tell us something about these growths of these specific HPQs. And again, the correlation, the correspondence between which pi 0 and which HPQ, there's a lot of complicated combinatorics there. So there's more like contest math problems to figure out what exactly this says about the HPQs. So this is what's slowing us down. And once we work out these, then it should be posted. Okay. So yeah, that finishes the section on results, and that's sort of right. So now I should sort of get into the background on this classification, unless there are questions. Okay. So I'm going to give a particular perspective on Arthur's classification that like is not the full totality of the classification and everything that it says, but the perspective that just like most quickly tells the story of the pieces that we need for this specific result. So in this perspective, the goal of Arthur's classification, you can think of it as trying to parameterize. You pick some reductive group G, and you want to parameterize discrete automorphic representations for G in terms of automorphic representations on GLN. So why would you want to do this? Why you would want to do this is there's a lot of known information about automorphic representations on GLN. So I'm going to focus on two things in particular. There's this McLaw-Walsh for J classification of arbitrary automorphic representations on GLN in terms of nice representations that are called hospitals. And there's also local Langlands, which you know for GLN. So you can transfer both these powerful results on GLN and you can get some kind of nice classification results for automorphic representations on G. So the endoscopic classification is usually stated in terms of two key concepts. So the first concept are things called parameters. And parameters are basically automorphic representations on GLN, but they're encoded in a certain special way that emphasizes this already known information. So the next key concept is a packet. So every parameter gives you a packet of automorphic representations on G, and this is some subset of the discrete automorphic representations, and there's a lot of information on the specific local components of this subset. So which G can we have? Well, by Arthur, we can have G equals S01 or SB2N. By Mach, we can have G being a quasi-split unitary group. And then finally, the case that we're actually going to use here, we can look at general ring unitary groups by work of Coletta, Mingus, Shin, and White. And of course, the big red warning applies here because all these results depend on certain things that are not published. Okay. So some details on what parameters are. So we can look and we can define something called an elliptic Arthur parameter for the quasi-split unitary group of rank n. And this is going to be a formal sum that we just write as a sum of some tau i's brackets some di's. So each tau I is going to be an automorphic representation of GL Ti of some number Ti. And it's going to be conjugate, self-dual, and cuspal. These are just some adjectives you can add to it. So conjugate self-dual, there's some like conjugation and some transpose action on the unitary group. So you can twist the representation by this and you should get the same thing. And basically the product of the sum of these products of Ti times Di needs to equal the rank of the unitary group. Okay, so every Arthur parameter determines local parameters basically by local Langlands. You have to do some extra thing, but it's basically by local Langlands. And we think of these local parameters as a map from a certain Langlands group at the local place times SL2 to the L group of this unitary group. And what it is we apply local Langlands basically to each of these cuspal parts. And then we just, we tensor with the Di dimensional representation of SL2. So these DIs are sort of like a Di dimensional representation of SL2. That's kind of what they are intuitively. So this is sort of like a very brief, like quick thing of what a parameter is. So next, let's talk about some details of what these packets are. So basically, the main theorem of the classification is that the discrete automorphic representations of G break up into they get partitioned into subsets for each parameter. So we're going to let G be some inner form of this quasi-split unitary group, and then to each elliptic parameter of this quasi-split unitary group, there's an associated packet of discrete automorphic representations inside G, such that when you union together all these packets, they're all disjoint, and their union is all discrete automorphic representations. So just to make sure that like things being disjoint means like they're disjoint realized as functions in L2. So I write this disjoint union as like a trace identity, where you take some functions, you trace it over the entire discrete automorphic spectrum. It sums into traces against each packet, and the trace against each packet is a sum of traces against the representations of the packet. So remember this I psi over here, this is going to come up again. That's just the sum of the trace of the trace of a function against all representations in a given packet. So this pi psi, this packet determined by psi, is furthermore, it's a subset of a restricted product of local packets pi psi v that are determined by the psi v's, and which subset it is determined by something called a multiplicity formula, which I guess I've mentioned before when explaining the zero, but there's some rule that tells you whether something's in here or not. And these guys are infinite, but like if you plug in a specific test function, you're going to kill all but finitely many of them. So that's the details about packets. So I don't know whether this is probably like too fast to be useful to anyone who hasn't seen this before, but hopefully there's something that's helpful here. So we need two more pieces from Arthur's classification. We need to talk about something called the stable multiplicity formula. So, okay. So these I psis, I defined them before, but you can also, well, they're originally defined as pieces of the discrete part of Arthur's invariant trace formula. So that's just something. And there's also a stable trace formula that Arthur defined, and there's a discrete part of that. And we get S psis that are summands of the discrete part of the stable trace formula. So if you don't know that already, the key point here is that there's a result called stabilization that works at the level of these I psis and S psis. And the point is we can write I psi as a sum of S psis on smaller groups. And these smaller groups are called endoscopic groups. So we're going to do an induction later. And this is going to be part of the induction, like breaking up the I psi into S psis on smaller groups. So the other point is that these S psis, they have an explicit formula. that, well, the explicit formula is usually written differently, but I'm going to break it up into 3 pieces. So there's an epsilon, there's a C, and there's a trace. So this epsilon is a very difficult sign attached to psi. It's extremely difficult to compute. The C psi is a very easy constant to compute. It's just some it's again just some combinatorial formula. And this trace is it's a stable trace associated to a packet. So this is some signed sum of the traces of representations inside the packet. And these signs are determined, and I don't want to get into the details of what they are. And the key point of that is that the stable trace is related to a trace of another representation on some twisted GLN, which is maybe you can just think of it as GLN semi-direct product of Z mod 2, and you extend the representation to the semi-direct product. And this pi psi is explicitly described as a Langlands quotient of the pi's for the tau i's that make up the psi. And well, it's explicitly described, but you need to also describe the twist, and the twist is very complicated. So this is the stable multiplicity formula. So these are things that'll come up when we actually explain the inductive technique. And it's just, I don't know. Again, it's probably too much.
What do you mean by the twist again?
So the twist is so the twisted GLN, you think of it as GLN semi-direct product of Z mod 2. So if you have a representation of GLN, then if it satisfies some properties, you can think about extending that representation to the full group. You extend it to the non-identity coset, and that's what I mean by the twist.
Okay, thanks.
Yeah. Okay, so finally, we need to talk about a special kind of packet at infinity. So our representations at infinity are special. They're cohomological representations. So they lie inside special kinds of packets. So these special packets are called Adams-Johnson packets. So basically these parameters psi infinity at infinity have associated infinitesimal characters. This is an invariant of real representations, and that's sort of the invariant of all the representations that are in the packet. So if the infinitesimal characters has these adjectives, regular integral that it satisfies, then the packet is something called an Adams-Johnson packet. And the key upshot of this is that there's an explicit combinatorial description of all the representations inside these packets. So not only is there an explicit combinatorial description, but these are exactly the packets that contain cohomological representations. And every cohomological representation only appears in these packets. So they're all cohomological, and they're the only ones that have cohomological things. So I need to give a caveat here that this explicit combinatorial description is actually, well, there are 2 definitions of Adams-Johnson packets. There's the original one, and there's the one that comes from Arthur's classification and these endoscopic classification papers. And it's not at all obvious that those 2 descriptions are equal to each other. But I think this work was completed very recently, that they're actually equal to each other in all these cases. So now we can just black box it. So saying that there's an explicit combinatorial description of elements is hiding a lot of very difficult real representation theory. But as of maybe a few months ago, it's all done. So we're happy with this.
Unitary case of this, did you?
The unitary case, Aaron Stivia.
Oh, they also do it.
Yeah, they also, yeah.
Oh,
And I guess, yeah, someone told me that it works for the non-Clausius split things also. So.
okay.
Yeah. Okay, so there's a key property that we need to use for these Adams-Johnson packets that maybe isn't emphasized a lot. So this key property is that for every cohomological pi 0, there's a specific function called a pseudo-coefficient, such that among all the pi that share an Adams-Johnson packet with pi 0, tracing against this function exactly picks up pi 0. So basically, we can't construct a test function that picks up pi 0 amongst all unitary representations, but we can pick a function that picks up pi 0 amongst all unitary representations that share an Arthur packet with it. So this is a very important thing for our method, and this is what we're going to try to abuse. So basically, for the people that know, the pseudo-coefficient is going to be the pseudo-coefficient of a discrete series that appears in the character formula of pi 0. You can pick any pseudo-coefficient of any discrete series that appears in the characters formula of pi 0, and that'll work. Okay, so that was just a very quick rush through all the background on the endoscopic classification that we need. So now let's describe the specific inductive analysis and how we use all of this. So first I need to sort of lay out all the key players and the parts that will come into this inductive analysis. So first we need Arthur's invariant and stable trace formulas, these distributions that you can plug in F and you get sums of traces. And we need their parts for specific Arthur parameters. Okay, another thing we'll need is Arthur's simple trace formula. So there's a specific test function you can plug in at infinity, such that when you evaluate the invariant trace formula with this test function at infinity, you get a literal sum over discrete automorphic representations with the correct infinitesimal character of the trace against that automorphic representation. This coefficient at infinity is like easy to deal with and not a problem. And there's also a similar result for the pseudo coefficient from the last slide, that it literally decomposes as a sum of traces against representations. So another thing we're going to need, this is going to be our input at the very bottom of this induction, is Shin-Templier's analysis of the geometric expression for plugging in the specific test function. And Shin and Templier were able to bound this extremely explicitly. And this is where the error term from the main theorem comes from. So at the bottom, there's this bound with this error term, and then we just need to preserve the error term all throughout the induction. And then finally, we need to plug in a specific test function away from infinity. And we're going to use this specific test function over here. So the trace against it is this term that you remember from being inside the sum of the main statement. So these are all our players. Okay. Now, this inductive analysis will depend on a key definition that we're going to call refined shape. So if you have an Arthur parameter, remember we wrote the Arthur parameter as these tau i's, bracket these di's, this formal sum. So if we have an Arthur parameter, then the refined shape of it is basically a series of triples, ti, di, lambda I, where ti is going to be the dimension of this tau I, so it's a cuspidal automorphic representation for some GLTI. Di is the same di as before, and lambda I is going to be the infinitesimal character of the infinite part of each of these tau i's. So this is some invariant of the Arthur parameter. And the key property of this invariant is that if you know that these lambda i's are all regular integral, then delta determines psi infinity for every packet psi that has this invariant delta. So this is some kind of invariant that remembers what psi infinity is. And that is the main thing that's going to be useful here. So basically what we're going to do is we're going to get some kind of expression by this induction for the part of the trace formula that corresponds to representations with a given shape. That's a part of the trace formula that corresponds to representations with a certain packet at infinity. And that's what's going to let us plug in the test function and pick out exactly the representations with the pi 0 at infinity. So let's be more formal there. So we make a list of all the Adams-Johnson parameters that have this pi 0 in their packet. Then we're going to look at the list of all the shapes for each of those that correspond to that specific parameter at infinity. And we're going to take a union over all of those. And that's a set of shapes that's determined by pi 0. All the shapes that allow pi 0 to be the infinite component of an automorphic representation in a packet of that shape. So, right, then of course, the sum of all the automorphic representations with this thing at infinity is going to be the sum of plugging in the pseudo coefficient from that Adams-Johnson packet slide into the invariant trace formula for the specific shapes that allow this thing at infinity. Because every other infinite component in things of this shape is going to share an Arthur packet with pi 0. So it's going to be killed when you plug in the pseudo coefficient. So you're only going to be left with the things that have pi 0 at infinity when you plug this in. And right, of course, the thing of the term with a given shape, I use the subscript to mean just the sum of all the packets that have that shape. So of this I psi from before. Okay, so that's our first step. So our goal now is to be able to evaluate this thing over here. Okay, so now we can do one more thing. There are two techniques that I don't have time to get into. So sort of like they're called stabilization and hyperendoscopy that let us sort of switch freely between the I delta and an S delta that's defined similarly. And basically what happens is you end up using that stabilization result from the stable multiplicity slide. And you add a bunch of terms on smaller groups. And those terms are going to be smaller order in this n. So they're going to be error terms. So we can just sort of freely switch between these two. So our final goal after doing all of this is we need to understand S delta, plugging in an Euler-Poincare function and our specific test function away from infinity for shape for some specific shapes delta. So that's our first step, and that gets to this goal. And achieving this goal is where the induction comes in. Okay, so I'm not going to explain how the induction fully works. I'm going to first talk about sort of a heuristic dream of how we want the induction to work. So first of all, we're going to isolate a very special shape. And this is going to be, well, we're going to call it the trivial shape of like rank T. And what this is you fix an infinitesimal character. And this is the shape that corresponds to like, there's a sum of tau I di's. So the sum is just a single term and the di equals 1. So these are the parameters that correspond to cuspidal automorphic representations on GLN. So we have this trivial shape. So we can find the part of the stable trace formula for the trivial shape by taking the entire stable trace formula and subtracting the parts for all the other shapes. So this is some like total triviality, right? We only care about one thing, we just subtract away everything else. So then the next part is we need to reduce the terms for other shapes to terms for the trivial shape on smaller groups. So if we can do that, then we can build up everything in terms of this SH. We're allowed to freely switch between the SH and the IH. Shin-Templier tells us how to bound the IH, and then we can bound S of everything. So how do we do this reduction? Well, the reduction comes in 2 steps, and these 2 steps are dreams. They're very difficult. But the first dream step is we need to be able to do something called stable transfer, where what we need to do is we look at the trace against something of the shape that's a sum of a lot of things. We need to write it as a product of a trace against each of the individual things with a specific function over here. So we need to be able to, given an f, we need to be able to construct fi like this. The next dream step we have to do is something that I'll just call space transfer, where we need to be able to get rid of the di and by changing this up into something else. So if we know how to construct both these stable transfers and space transfers, then what we can do is we can write SH for a complicated shape in terms of SH for trivial shapes. So we put this and this together. S for any shape is just some complicated linear combination of products of these SHs. We turn them into IHs, we substitute in Shin-Templier bounds, and then we're done. Okay, so of course, in reality, these stable transfers and space transfers, doing them explicitly, these are very difficult open problems in general.
I'm sorry, are you completely done with the induction step? Because if you're doing it on one variable and you have 4, shouldn't you be doing it on every single one?
Well,
Also
the point
T
is,
and then lambda and
yeah, so the lambda is kind of fixed by this EP that we're plugging in. We're only inducting on the T and the D. So this thing over here tells us how to reduce the T's and the D's, right? And the lambda's determined by this thing over here, the lambda inside this Euler-Poincare function. And this last variable is just like a technicality. It doesn't really, it's like something you have to put in just because of like there are 2 ways to realize a unitary group as a twisted endoscopic group, so you need to keep track of that, but it's not really important for this induction. I don't know, sorry, maybe that wasn't a satisfying answer again, but.
no, it's a good answer. I just feel like you have a limited calculation the way you're trying to do it. But maybe that's just me. I didn't actually do the calculation. So that's just my opinion.
Yeah, so it's even worse than you're saying because there are lots of T's, right? So like you have to break it up so that there's only 1 T and you have to reduce all the D's to 0. So this is like breaking up so there's only 1 term in the shape and this is like reducing the D's to 0. So that's sort of the 2 steps in the induction. And then you only have the T and the lambda to worry about. And just having the T and lambda to worry about, this like Euler-Poincare function deals with that. That's sort of maybe that's like a very big thing.
Okay, thanks.
Okay, so yeah, these are hard open problems in general. So basically the main work in the analysis is literally just to find an easy special case where we can compute these. And that's where all the restrictions in the theorem comes from, why we're looking at unitary groups, why we're only working at split level, why we want things to be unramified and everything like that, is that's just so we're in an easy case where we can compute all these stream transfers. And like, it's basically, this is like the easiest possible thing. This is the case where there's no hard work in computing these transfers. Like we didn't solve any difficult local problems. We just like tried to focus on a case where it's basically already known how to do it. So, I mean, the general idea is we can use relations to the twisted representations on GLNs and Langland's quotients to try to work these out. And the saving grace is that, well, among all these deltas, some of these deltas have dominant contributions and some don't. So we only need to compute these transfers exactly for the dominant contributions. And we're allowed to just like shove everything else in the error term if we have a strong enough bound. And I think I'll stop there.
I have two questions. One, you said that prove the conjecture of Xue and myself would mean some inequality with all your data.
Right.
Did you check with small numbers that it works out?
Yeah, we checked with small numbers that it works out.
It's quite close. You usually come just underneath our inequality, right?
Yeah. When we plotted it, we usually come just
underneath.
Yeah, just underneath. Yeah.
Okay.
And we have some guess of what the worst possible case is supposed to be, but again, it's like a map contest inequality, so we could be wrong with that guess. But like,
the other question I have is Rogowski, when he did this in unitary group in 3 variables a long time ago, constructed quotients of the unit ball, arithmetic quotients for which a first Betty number never switches on as you go through congruence groups. Can you now, I mean, maybe you're throwing all this in the worst case analysis, but if you take a unitary group in many variables, maybe this has been done by somebody else, can you show that there are examples where you go through congruence groups, and of course you'll have the congruent subgroup property true, so that'll be all finite quotients, that you don't switch on cohomology except in the middle or near middle dimension? Have you thought about that?
yeah, I think Mathilde was telling me something about that maybe some applications, but
that would be a nice application because it's like fake projective planes, but in higher dimensions, right? That cohomology does not get switched on, but because of Ramanujan, not because of unitary dual.
Right.
In other words, a unitary dual, Matsushima's formula allows you to have representations, but your transfer prevents it. So it's showing the arithmetic is preventing cohomology, and I think that was a very beautiful example of Rogowski, and it would be nice to understand it in general.
Okay, so because of these zeros, so maybe.
So it's a matter of choosing your unitary group carefully in your.
Right.
I mean, to be honest with you, I would just look at UN1.
Yeah.
And try make examples. Borel, so I think maybe Clausel wrote an example. Borel always felt that in this Borel-Wallach formula, you could always switch on a Betty number by going to a deep enough congruence, finite index subgroup. But that's not true. It's true in hyperbolic free space, as Agol showed us, but it's not true in general because of Ramanujan. So it would be nice to give high-dimensional examples of that, where you vanish. Yeah, you're not creating cohomology, except, but you're compact. So there's no. So your inner form be lovely. Anyway, Rogowski put a lot of effort into that in his book.
Okay, so thank you. That's a good thing to look at. So yeah, it won't be the asymptotic. You have to worry about all the shapes and all the parameters.
So this naive idea that Betty numbers are always switched on is just not true.
I think, I do think, Mathilde was.
I think, I think it's this moment where Rahul was like, the constant is 0. He's like, oh, sometimes it's non-zero, sometimes it's 0. I think in some cases when it's 0, at least some H1 is never going to appear.
That's my guess. You have the opportunity here to kill not just H1, but I think many.
Yeah.
Everything.
Be more careful about other degrees, but
lovely. Because it's the it's you. Non-tempered stuff doesn't want to be there.
Are there any more questions for Rahul? Great, then let's thank him again.